Today we're going to talk about filling orbitals and how to write the electron structure of an atom. So before we do that, just a quick reminder about orbitals. So an orbital is a region of space where you can have two electrons with opposite spins, and these are the regions of space where you're most likely to find them, as if you remember from a previous video, electrons can be anywhere in space, but physics has decided that 99% of the time they will be in these shapes. So an S subshell has a spherical shape and can hold a maximum of 2 electrons because it only has one S orbital. A P subshell has 3 p orbitals, which are a dumbbell shape on each axis, meaning it can hold a maximum of 6 electrons, 2 oppositely spinning electrons per orbital. So how do we actually fill the orbitals and know how to do it? So one thing we have to always remember is this little bit up here. In chemistry, any system wants to be in its lowest energy state. It doesn't matter what it is. Chemistry loves being in a low energy state. So how do you know which shell, like n equals 1, n equals 2, 3 or 4, is the lowest energy, and how do you know if S, P, D or F are the lowest energy? So the closer it is to the nucleus, the lower in energy it is, as it's more stable, because electrons are negatively charged and protons are positively charged, meaning they're attracted together a bit like magnets. So when we just look at the numbers 1, 2, 3, 4 and so on, number 1 means it's closest, number 2 means it's then the next shell out, number 3 means it's the next shell after that, number 4 means it's the next shell after that, and so on, meaning shell number 1, or n equals 1, is the lowest energy one of the numbers. So that means we would fill shell 1 before shell 2 and so on. So now if we look at the subshells S, P, D and F, subshell F is the furthest one away, while subshell S is the closest one to the nucleus, meaning S has the lowest energy. So if you remember the shape, S is spherical, meaning it's held really tight, whereas P is this dumbbell shape on each axis, meaning the electrons can actually just get a little bit further away than the S, meaning the p orbitals are slightly higher in energy than the S, however not high enough to overtake the 3s. So for example, 2p is still a lower energy than 3s, but a higher energy than 2s. So 1 is a lower energy than 2, lower energy than 3 and so on, and S is a lower energy than p, which is a lower energy than D, and so on. So, saying all this, there is one small change to this, and that's when you look at 3D and 4S, which I'll explain on the next slide after I've said what I'm about to say. So, the reason why the energy levels are different as you get further away is because once you fill up, say, this 1s, the 2s is being blocked by these negatively charged electrons in the 1s. Like I said, they're a bit like magnets, so if you try to put two of the same poles together, they're kind of repelled. So if you have electrons in the 2s, the ones in the 1s are repelling them slightly, trying to push them away. Not enough that they go off into infinity, just enough to keep them slightly further away than the nucleus, because the protons are still attracting them. And it's the same for the 3, it has 2 lots of shielding from the 1 and 2 shell, and 4 has shielding from 1, 2 and 3 shell, which is just explained by this bit down here in words. So how do we know which way to fill them? So there's this nice thing that you can be taught at A level, and that's drawing arrows through what I've written out here. So first of all, you'd fill the 1s, you draw it diagonally up, then you'd fill the 2s, then the 2p and the 3s, then the 3p and then the 4s, then the 3d and the 4p, and so on. You just draw the lines exactly the same each time, and each one it bisects is the one that you'd fill first. However, like I said, shell 3 and subshell D and the 4s, so the 3D and the 4s, are a little bit different. So by what I've said about 1 being lower energy than 2 and so on, and S being lower energy than P and D and so on, you would think that the 3D's filled before the 4S, but it's not. And the reason for that is university level. However, I can show you the energy sort of levels just to show you how close they are in energy. So when we look at this, you see there's a big gap between 3s and 3p, and that's similar between 2s and 2p, for example, and things like that. Now we would expect there to be a big jump to 3d again, and then there'd be a big jump to the 4s, and we would expect the 4s to be somewhere up here. But in fact it's not. In fact the 4s is actually just lower in energy than the 3d. This means that the 4s is filled up just before the 3d subshell. And again, the reasoning behind that is university level. I mean, you can Google it if you wish, but it's something that you will not need to know. It's that's with A levels. It's just sort of learning some facts without explanation, and if you were like me, an explanation actually helps a lot. But I won't go into it on this video because it will take a little bit longer than probably the rest of the video. So, just to remember, in chemistry, any system wants to be in its lowest energy state, meaning that if you filled up, you'd fill up the 3s first, then you'd fill up the 3p second, then you'd fill up the 4s, then you'd fill up the 3d, because the 4s is lower in energy. Interestingly, if you were to remove an electron to create an ion, if you have the 4s full, and say you had 1 or 2 electrons in the 3d, you would actually remove an electron from the 4s first, because when it's full, if we put F for full and F for full, you actually, so that's the 3s, and that's the 3p, that's the 3d, and now the 4s is actually just above. If the 4s is full, and that, I just put partially full, it's actually slightly higher in energy, which is really, really interesting again. So when you were to make an ion, say in the transition metal series, which you'll more likely cover in A2, you would remove this electron first, or the 2 electrons in the 4s. As you remember, an S subshell holds 2. You'd remove the 2 electrons from the 4s first before you'd go on to the 3d, even though you add them a different way around, so you add the 4s and the 3d last. I just thought that's a little bit I would mention. So now we're going on to actually filling orbitals. So to teach this, it's better to do some examples. So if we take carbon for this one, so how you fill these diagrams is, that's an electron with spin going up, and this denotes an electron with spin going down. So if you remember the definition of an orbital is an area of space where 2 electrons with opposite spins can pair up. So again, opposite spins, so this signifies going up, this signifies spin going down. Okay, so if we take carbon example, carbon has 2, 4, 6 electrons. So we start from the bottom. So first electron goes in here. Actually, I'll just write 6e minus there. And then when you pair up, this is an important bit to remember, when you pair up an electron with another electron in an orbital, because you've got 2 negatively charged things coming close together, again like 2 magnets on the same poles, they are actually repelled by each other a little bit. So if you can avoid pairing them up, you will fill each orbital with a single electron before pairing them up. But in this case, you haven't got another orbital, and pairing them up would cost less energy than putting it into the shell 2. So you would pair it up. It's only a little bit of gain of energy. If you would like to put numbers on it, these aren't exact numbers, but for example, it would be 1 kilojoule in energy, whereas the next shell up would be 10 kilojoules in energy, so it's better to pair up. In this case, when you get onto shell 2 to put in the next electrons, you'd fill the 2s, you would pair them up again, because the 2s is slightly lower in energy than p. However, when you get to p, you can have 6 electrons. So if we were to almost zoom in here on the p, we would have 1 p orbital, a second p orbital, and a third p orbital. Now, as it's got 6 electrons, we've filled 4 in. It's now a case of we've got to put another 2 in. So we put 1 in here, and you may be thinking, okay, let's just pair it up like the 1s and the 2s. In fact, you don't, because if you remember when I said you get a little bit of repulsion, it's actually better just to put it into another p orbital of the p subshell. So that's what we do. We put it into another one to minimize repulsion and keep it in its lowest energy state. Okay, so another example, if we do oxygen, which has 2 more electrons, so 8 electrons, and in this case it's the same, so we start with filling up the first 2 electrons in the 1s, and then you got the 2s, and again we split the p subshell into 3 orbitals, and because we've now got 4 remaining, a total of 8, we've put 4 in, we've got 4 remaining, you would in fact do 1, 2, 3, and then the 4th one would pair up. And remember with the previous example, you put them into each separate orbital first to minimize repulsion before pairing up. So that's what oxygen would look like. So you have a total of 8, so you would have 4 electrons in the p orbital. Now, how do you actually write the electron configuration? Not draw them out electron at a time saying how it fills up. So now you know that shell 1 is lower energy than 2, lower energy than 3, so on, and S is lower energy than P, lower energy than D, and so on, minus the 4s 3d kerfuffle earlier. So, as we know, carbon has 6 electrons, and as we said, we could fill them up 1s first, then the 2s, then the 2p, and so on, exactly drawing them out. You can draw it out first if it makes it easier. But how you write it is, if you fill up the 1s first, you write, okay, 1s, and how many electrons there are in there. So there can be a maximum of 2, and we've put 2 in there, so 1s, and then superscript 2. Then with no spaces, we go 2s, as we're filling 2s up, with a superscript 2, because we've put 2 electrons in there. Now 2p is next, however this time we've only put 2. You can have a maximum of 6 p electrons in there, but we've only put 2, so again 2. So that counts for the 6 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6 electrons. So we've placed them in the relevant energy levels. So now if we take potassium, potassium has a lot more electrons. So again, we fill up the 1s with 2 electrons, the 2s with 2 electrons, the 2p with 6 electrons, so that will take us to neon. Then we also fill the 3s with 2 electrons, as the maximum can be 2, and then we've still got this row with aluminium, silicon, phosphorus, and so on, meaning 3p also contains 6 electrons, and then it's potassium, so we're now on to 4s. Remember, we fill up the 4s before the 3d, and as you remember from my previous video, that these are the s block outer ones, and we haven't actually filled any of the d electrons yet. So potassium has 1 electron in the 4s, so we just put superscript 1. And it's as simple as that. So you write principal quantum number, n, which is, or shell, as you may refer to it as 1, 2, 3, 4, and so on, first, and then you put the subshell you're filling up, so S, P, D, or F, and then you put the amount of electrons that are in that subshell, and as a superscript, and it's as simple as that. So if you had something with D electrons, you might just write D10 for zinc. You would have 4s, 4s2, and 3d10 for something like zinc, because you would have filled up all the 1s, all the 2s, you would have filled up the 3s and the 3p, and you would have filled up 4s, because 4s is filled first, and you would have filled the 10 up to zinc. So 4s2, 3d10. So I hope you liked the video, and I've hoped it's helped with your revision or learning for A-level chemistry, or anyone who's interested in chemistry in general. Please like, share and subscribe, and if you would like any specific videos, just leave a comment below and I'll be as quick as I can with creating one.